So we're in section 6.3. All right, so vectors, what we're interested in with vectors is we're working with quantities that have both a magnitude our quantities have both a magnitude and a direction. So examples of things that have magnitude and direction are, we could think of position. So position, we think we want to, when we're talking about bearing, we say we're at this point and we're at 30 degrees north of west. So we have a position and we have a direction. We know how far we've traveled and we know where we are. So a position would be an example of a vector. It has a magnitude, how far we are away from something, and what direction we're away from something. Velocity is a vector. We're traveling 20 miles per hour in a specific direction. So magnitude and direction would be, velocity would be an example of something that has magnitude and direction. Force. We're pushing with a certain force on something in a specific direction. So those are examples of things that have magnitudes and directions. We need to know both how strong the force is, how fast we're going, and in what direction that the force is pushing, or the direction that we're moving. So we can think of vectors as, the way we think of them, the way we visualize them, is a directed line segment. And we usually draw a vector as an arrow. So there's my vector. We put an arrow at one end. That tells us our direction. Couple of pieces of terminology. So if our vector starts at point P and it ends at point Q, we call this the initial point. And point Q is the terminal point. And we would call this vector, the arrow, we would call the vector a vector PQ. And we put this kind of one-sided arrow over the top of our lines to show that it's a vector. So we would call this vector PQ, initial point and terminal point. Now in the book, and when you see vectors in print, vectors will be shown with bold letters. The way we'll write them in class is we'll say, just because I can't really write in bold, we'll say vector A with a little arrow over it, or vector B. So these would be vector A, vector B. So we'll use the little arrow to show that we're talking about a vector. In the book they use bold print to show that they're talking about a vector. So the arrow, this gives us an idea of the direction. We're going to talk about the magnitude. The magnitude or length of a vector is written, we would write the length as we put these double braces. In the book they use double braces. When I write it up here, I'm going to use just single bars, like the absolute value sign. So if we think of the absolute value, if we think of it as an absolute value, this is our length, or the magnitude. We call it the magnitude of our vector. That just tells us how long this line segment is. So our vector has an initial point, a terminal point. We use this little half arrow to show that we're talking about a vector. and the double bars, or in the book you'll see the double bars. I like to draw the single bars because when we start writing a lot with lengths, the double bars end up getting kind of messy. So that's our terminology for vectors. We say that vectors are equivalent, or they're equal. If and only if they have the same length and the same direction. So what that means, what we're saying is, if we have a vector here, and a vector over here, as long as they have the same length and they point in the same direction, we call them equivalent. It doesn't matter where they're located, as long as they have the same length and same direction, they're equivalent. If I can move one of these on top of the other, and they have the same length and they're pointing in the same direction, they are equivalent. Doesn't matter where they're located. The location doesn't matter. So let me do a quick example talking about the length, the magnitude, and the direction of a vector, just to show how we work with these. So if we have v, and I make my v's with a little tail because my v's end up looking a lot like my u's. So v is the vector. From 0, 0, point 0, 0 to the point 4, 5. And u is a vector from 2, 3 to the point 6, 8. We want to show that these two vectors are equal. So to show that they're equal, we want to show that they have the same length and they point in the same direction. So how can we show that these vectors that go from this point to this point, from 0, 0 to 4, 5, and from 2, 3 to 6, 8, how can we show they have the same length? What would we use? Distance formula. So we can find the distance from point 0, 0 to point 4, 5. So we're going to calculate the length. Basically, we're calculating the length of these segments. So the length of v, we use the distance formula, is 4 minus 0 squared plus 5 minus 0 squared and this gives me the square root of 41. 25 plus 16. The length of u, using the distance formula, is 6 minus 2 squared plus 8 minus 3 squared. And that gives me also the square root of 41. So we know that they have the same length. How are we going to show that they are pointing in the same direction? What would tell us that they're pointing in the same direction? What do we think? So we want to know they're moving in the same direction. We want to know that. So if we have, so let me draw two vectors here. Oh, that's not what I wanted to do. If I draw two vectors here, and let's say that's u, we know they're the same length, and if these two vectors are going in the same direction, what does that say about these two segments? How are they related? They're parallel. If they're parallel, what the slope, there we go. If they're parallel, their slopes are the same. So we can figure out the slope of the segment between these two lines, or between these 2 points, and see if they're the same. That would tell us if they're in the same direction. If they're going in the same direction, they're going to be parallel. The slope of V is the rise over the run, 5 minus 0 over 4 minus 0. The slope of V is 5/4. The slope of U is 8 minus 3 over 6 minus 2, which is 5/4. They have the same length and they have the same slope, so they are equivalent. They have the same length and they're going in the same direction. So same length, same direction. So they are equivalent. Yeah, Kevin.
You have to do like the 4 minus 0 squared.
What?
You just do 5 minus 0.
I'm sorry. Can you just do?
You just do like 4 minus 0 and 5 minus 0. You have to do like the 4 minus 0 squared.
If as long as you figure out that this part under the square root is the same, but you do have to use a distance formula to make sure they're the same. I wouldn't have as long as I knew that this was 41 and this was 41, that would tell me that they were the same. But we do have to use a distance formula to figure out that they're the same length. All right, questions on when vectors are equivalent and about the length of a vector. All right, so vectors just tell us we have a certain length, we're moving in a certain direction. Yes? Distance formula, sure. Distance between 2 points is x2 minus x1 squared plus y2 minus y1 squared, and that's for points x1, y1, x2, y2. So that's a distance formula between 2 points. And it comes from the Pythagorean theorem. All right. The next thing we want to talk about is the component form of a vector. And this is how, a lot of times, how they're going to be more useful. So what we're interested in with the component form of a vector is we're going to figure out, we're thinking about part of it pointing in the x direction and part of it pointing in the y direction. So we're just breaking it down. We're thinking of a vector essentially. If I draw a picture here, what we're doing is we're breaking this vector down into a part that points in the x direction and a part that points in the y direction. So if this is my vector, we're breaking our vector into this part and this part, and we're saying that our vector is these parts added together. Our vector, so for the component form, we say that a vector is in standard position, and the book will, sometimes you'll get problems that ask you about standard position. So standard position just means that its initial point is at the origin. And the origin again is the point 0, 0. Doesn't matter if it's going up or down. We just put that initial point at the origin, and that gives us our standard position. And because we said that vectors are equivalent, as long as their length and direction are the same, it just is convenient to have the initial point at 0, 0. It makes things easier to calculate. So if our vector is in standard position, its initial point is at the origin. So if we have vector v, so v is a vector in standard position, we're going to say that its terminal point, so its initial point is 0, 0. And we're going to say its terminal point, so at the tip of the arrow, is at the point v1, v2. So what we have is our vector, if this is vector v, this is 0, 0. We're in standard position. And this point up here is the point v1, v2. So that's what we're talking about. So if we have our vector in standard position, we say that v equals, and we use these little pointy brackets, v equals the vector v1, v2. And what this is telling us is that the terminal point is v1, so we've gone over the length of this side of the triangle is v1. And the length of this side of the triangle is v2. So we've gone over to the right by v1 units, and we've gone up by v2 units. So we use these pointy brackets to say we've gone over v1 and up v2. So this is what we call the component form of the vector. Is there a question? No questions? And if we have our vector, if our vector goes from some other point than 0, 0, if v is from x1, y1, some point x1, y1, to x2, y2, then our component form is just x2 minus x1 comma y2 minus y1. So if this point is not at 0, 0, so I'll redraw this picture over here. So here's my vector. What we're talking about here is that my initial point is x1, y1. And my terminal point is x2, y2. Then this side of the triangle is x2 minus x1 units long. And this side of the triangle is y2 minus y1 units long. So that's all it's telling us. We can break our triangle into these pieces. How far do we go left and right? How far do we go up and down? That's really all this is telling us. How far left and right, how far up and down. Questions on the component form? If you think of your vector, if you think of these little triangles, that's really what we're doing with the component form of a vector. All right, let's look at an example using component form. So we want the component form of the vector from the point 2, -4 to 5, 7 and its length or magnitude. So if we call this vector v, we say v, call this vector v. Our component form is just going to be x2 minus x1, 5 minus 2, and y2 minus y1, 7 minus -4. So I get the vector 3, 11. So that would be this vector in component form. I go 3 units to the right, and I go 11 units up from this point to this point. That's what it's telling me. The magnitude, or the length of v, is just the square root of 3 squared plus 11 squared. So this is going to give me the square root of 130. So when I have my vector in component form, I just take the square root of the first part squared plus the second part squared. Yes? It would really depend on the problem. On some of them, if it asks for it rounded to 2 decimal places, whatever, then you could put it in your calculator. I'm fine with it written like that. If you want to simplify the radical with the rules that you know about simplifying radicals, that's fine also. Okay? So to find the magnitude of a vector in component form, all we have to do is take the square root of the x component squared plus the y component squared. If the magnitude of a vector equals 1, we call it a unit vector. So a unit vector is just a vector with length 1. A vector with length 0 it is called the 0 vector. And the 0 vector we write as 0 vector, or as 0, 0. So 0 vector is a vector with 0 magnitude. 0 vector is not the same as the number 0. A vector is not the same as a number. So if we have a unit vector, that means its length is 1. The 0 vector means it has length 0. And it's important to remember that the 0 vector is not the same as the number 0. All right, questions so far? With our component form, we have what we call standard unit vectors. The standard unit vectors, our standard unit vectors are I, and we put a little hat over it. to tell us it's our standard unit vector. And we can call it I hat. Our standard unit vector I is 1, 0, and j is 0, 1. So these are just a vector in the direction of the x-axis with a length of 1, or in the direction of the y-axis with a length of 1. So we can write, what we use a standard unit vector to do is if we have the, for example, if we have the vector 3, 5, we can write this as 3i plus 5j. This tells me I'm going 3 units in the x direction and 5 units in the y direction. So I can write any vector as a combination of some number times the standard unit vector in the x direction plus the standard unit vector in the y direction. So 3, 5 is 3i plus 5j, negative 2, 7 would be negative 2i plus 7j. So this just tells us we're going negative 2 units in the x direction and 7 units in the j direction. So we can write any vector in the plane as a combination of i's and j's. All right, to save some writing,